Hi everyone, this is lecture 4 of my series of lecture for students in statics. So we'll discuss in this video the vector operations. It's all about vectors. So we have dot product, cross product, and scalar triple product. So a vector may be represented by any of the following ways. So we have a boldface symbol, quantity, then we have here the x, y, and z components, and the partners are respectively the ijk or the unit vectors along x, y, and z. And the other one is boldface, then the components are placed inside the parentheses. The magnitude of vector A is represented by absolute value of A, which is the square root of ax squared plus ay squared plus az squared. So the first vector operation is the what we call dot product, and its uses would be to determine or compute the component of one vector in the direction of the other and vice versa. Also, it allows us to determine the angle formed between two vectors. So addition and subtraction of vectors. Two or more vectors can be added or subtracted by adding or subtracting corresponding components. So for example, if vector A is given by this expression, vector B is given by that expression, then A plus B or A plus minus B is quantity AX plus minus BX I, then quantity AY plus minus BYJ, then quantity AZ plus minus BZK. In this case, we have A minus B, and it is the difference of corresponding components. Product of vectors. We have the dot product, which is a scalar product. So the result is a scalar. And we have A dot B, which is equal to AB cosine of theta, where A and B are vectors in the left side. Then in the right side, we have magnitude of A, magnitude of B, and cosine of the angle between them. So with respect to the product of unit vectors, I dot I, therefore, using this formula is 1, magnitude of I is 1, magnitude of J is 1, I is 1. Then cosine of the angle between unit vectors I and I is 0, and cosine of 0 is 1. Therefore, it is 1. If you dot I with another orthogonal unit vector, then the result is 0 because cosine of the angle between them is cosine of 90 is 0. So j dot j is also 1, k dot k is also 1, and I dot j is 0 equals j dot I dot k is equal to k dot I, 0, then j dot k equals k dot j, 0. By the way, that product is commutative. So if these are the two vectors A and B, and this is the angle between them, then one application of the dot product is to determine the component of one vector in the direction of the other. We call it the orthogonal component of vector A in the direction of B, denoted by A sub B, and it is a scalar. So if you treat this as a right triangle, then A sub B is simply hypotenuse, which is the magnitude of A, times the cosine of the angle between them. So A sub B is A cosine of theta, and it is equal to the dot product from this result, because A sub B is equal to A cosine theta. From this formula here, A cosine theta is A dot B divided by magnitude of B. So likewise, we can also compute the projection of B, scalar projection of B onto A, or the component of B onto A in the direction of A. So this is another right triangle. The hypotenuse is the magnitude of B. The angle between them is theta. So this is by trigonometry B cosine theta, and this is B sub A, the scalar projection of B in the direction of A, and it is B cosine theta. And from this formula for that product here, B cosine theta is A dot B divided by A. So take note that A and B are vectors denoted by the arrowheads, and the denominator is a magnitude. So that's it. Now, we can also express this scalar component of one vector in the direction of the other into vector form. So all you have to do is multiply, for example, if you want A sub B to be in vector form, vector projection, then you multiply this by the unit vector of B. Likewise, if B sub A is required to be in vector form, then we multiply that by the unit vector of A. So here it is. This is the vector projection of A in the direction of B. So all you have to do is multiply or uh, obtain the dot product of its magnitude with the unit vector of that direction. So in formula, because lambda of B or unit vector of B is vector B divided by B, so the denominator becomes B squared. Likewise, B sub A in vector form is equal to A dot B over A times lambda of A, or the unit vector of A. So it is A dot B dot A divided by A squared. So the vector projection of B onto A. The unit vectors are lambda A equals vector A divided by its magnitude, and lambda B is vector B divided by its magnitude. So let's have this right thumb rule. So this is the right thumb rule. You curl your index finger A to the long finger, then your right thumb will be pointing that result, that product as a result. So it is a vector. It is another vector perpendicular to the planes of A and B. So therefore, A dot B, A cross B, later A cross B is not equal to B cross A, because for A cross B, when you curl your index finger towards the long finger, then your right thumb is pointing the above direction. But if you curl B towards A, then your forefingers will be pointing in the opposite direction. So A cross B is not equal to B cross A. It is the negative of B cross A. That's the result. So I want you to remember that result. With respect to moment, so you position your right thumb towards the positive x-axis. The curling of your four fingers would be the positive sense for moment about x-axis, and that is that positive sense. About y also, you position your right thumb, then the curling of your four fingers would be the positive sense of moment about the y-axis, like that. Then position your right thumb towards the z-axis. The curling of your four fingers would be the positive sense for moment about the z-axis. That's it. So next we have the cross product or the vector product. So the result is really a vector as indicated in this right thumb rule here. So A cross B is equal to AB sine of theta. Now, because this is a vector, the interpretation of this or the magnitude of A cross B is simply the area of the parallelogram formed on the vectors of A and B. So if vectors are represented by line segments, directed line segments, then A cross B is another vector which is perpendicular to the plane of these two directed line segments. So with respect to the unit vectors, when you position your four fingers towards the I direction, positive I unit vector of x axis, then curl it towards J. Your forefingers will be pointing towards K. So I cross I is 0 because 1 times 1, if you use the formula, the angle between them is 0. Remember, I dot I was 1, but I cross I is 0. So J cross J is also 0 because the angle between J and J is 0 and sine of 0 is 0. K cross K is also 0. I cross J, you look at you position your forefingers towards the I direction, then curl it towards the J direction. Your right thumb will be pointing the K direction, so it is equal to K. So that's it. So you have here the counterclockwise curling, because that's the positive sense of moment also. So I cross J is equal to K, while J cross I is negative K. So to get this result, just position your forefingers towards the positive unit vector, the first one, then curl your forefingers towards the second unit vector. Your right thumb will be pointing the negative K direction, so it is negative K, J cross I. Then J cross K is equal to I, J cross K is equal to I. Forefingers towards the J axis, J direction, then curl it towards the unit vector K. Your right thumb will be pointing the I direction. So it is I, J cross K is I, while K cross J is negative I. And finally, K cross I is equal to J, that one. Then I cross K is equal to negative J. So that's it. The area of triangle defined by vectors A and B is 1/2 the product of the adjacent side times sine of the angle between them. Therefore, doubling that area is the area of the parallelogram form, and therefore the interpretation is A cross B, the magnitude of A cross B, because this is a vector, is the area of the parallelogram form on the vectors of A and B. So you position your forefingers towards A, curl it towards B, then it will define another vector A cross B, and the magnitude of A cross B is this area of this parallelogram. So the magnitude of A cross B is the area of the parallelogram. Then scalar triple product. This is used to compute volume of para rhomboid, like here, prism. Then remember that A cross B is equal to the area of the parallelogram. Then if one edge of the rhomboid is, let's say, vector represented by vector C, then you can compute the height or the distance, perpendicular distance between bases of a rhomboid, and that is dotting A cross B with C, because the result is magnitude of A cross B, magnitude of C, times the cosine of the angle between these two vectors, which I indicate beta. So we will call the altitude as h, so that's beta. So if we obtain the dot product of A cross B and C, we will have an expression for the height of the rhomboid. So this is the rhomboid. And remember, volume is area of the base times altitude. So volume of rhomboid is area of the parallelogram times the altitude. So to obtain that altitude, we simply obtain the dot product of A cross B with C, because the expansion would be magnitude of the first vector, which is represented by A cross B, times the magnitude of the second vector times the cosine of the angle between them. Remember, A cross B, absolute value of A cross B is area of the parallelogram, and C cosine beta in the figure is the altitude of this rhomboid. So therefore, the interpretation, it is it is the volume of the rhomboid. So scalar triple product therefore is a scalar. And if you want to express that scalar as a vector, then we have to obtain the dot product of that scalar magnitude with another unit vector of certain direction. So A cross D is AXI plus AYJ plus AZK. These are unit vectors. Cross BXI, BYJ plus BZK. Remember that I cross I is 0, so we only have AX BYJ because I cross I is 0, but I cross J is equal to K. Remember? So we only have value when we cross vectors of different unit vectors. So the expansion will be AX BX by commutative law of multiplication over addition. So we have AX BX I cross I plus AX BY AX BY I cross J plus AX BZ I cross K, then plus AYJ or AYBX J cross I plus AYBY J cross J plus AYBZ J cross K plus AZBX K cross I plus AZBY K cross J plus AZBZ K cross K. And remember that cross product of same unit vector is 0. So this is 0, this is I cross J, so the result of I cross J is K. Then I cross K is equal to negative J. So 0, AYBYK, AYBZ, negative J. Then J cross I is negative K. We have here J cross I is negative K. J cross K is 0. J cross K is I. Then J cross K is I. Then K cross I is J. K cross J is negative I. Then K cross K is 0. So this is, we have I, we have J, and we have negative I. So combining like terms, A cross B is equal to AYBZ minus AXBZ quantity. AYBZ minus AZBY quantity I, which is that. Then for J, we have quantity AZBX minus AXBZ J. Then for K, we have AXBY minus quantity AXBY minus AYBX K. So that's the result of cross product. But if you don't want to expand the cross product using this guide, if you want to expand it without thinking of the guide, then it's like evaluating the determinant of a 3 by 3 matrix. So you write the components of the first vector, then components of the second vector, then the unit vectors. Then by expansion, by basket method, we have to copy the elements of the first two columns. Then remember, getting the product of diagonals down to the right is positive, then up to the right is negative. So that's it. So for I, AYBZ, which is that, then minus in that direction, which is AZBY, then AXBX minus AXBZ J, then we have AXBY minus AYBX quantity K. So that's it. Expansion. A dot B on the other hand is AXI plus AYJ plus AZK dot BXI plus BYJ plus BZK. Remember that we only have, that product of unit vector, the product of a unit vector with itself is 1. The product of a unit vector with another orthogonal vector is 0. So therefore, we can easily expand this. This is simply the sum of product of corresponding components, because we have ax, bx, I dot I, which is 1, ay, by, j dot j, and az, bz, k dot k, which are all 1. Then I dot j, I dot k, zeros, and vice versa. Then for the scalar triple product, this is the expansion. You copy the elements of the or components of the first vector, then components of the second vector, then components of this last vector, then copy the elements of the first two columns, then follow the sign convention, just like evaluating the determinant. Positive down to the right, minus up to the right. So let's have this example. For the system of concurrent forces shown below, determine the magnitude of the resultant force, then determine the angle that the resultant makes with the y-axis. These are the forces in newtons. So simply the magnitude of the resultant force, we have to obtain the resultant force in vector form, and that is simply obtaining the sum of corresponding components, F1, F2 plus F3. So R therefore is equal to 3 plus 7 plus negative 6i, and 6 plus 4 plus negative 4 plus 14 quantity j, and quantity negative 10 plus 3 minus 8k. So simplifying, R is 4i plus 16j minus 15k newtons. That's the resultant in vector form. The magnitude is simply square root of 4 squared plus 16 squared plus 15 squared. So R therefore is equal to 22.29 newtons. Then for the angle that the resultant makes with the y-axis, then simply it is cosine of theta y equals ry over r. So let us show here that cosine of theta y is really ry over r, or y component of resultant divided by the magnitude of r. And let us show it by this dot product application. So r dot lambda of y, unit vector of y, is equal to magnitude of r, magnitude of lambda y, which is a unit vector, which is 1, times cosine of the angle between them, which is cosine of theta y. Substituting the value of r, which is quantity rxi plus ryj plus rzk, that unit vector y is j, is equal to r times 1 cosine theta y. But remember that the only defined dot product here is j dot j. The rest would be 0. So ry j dot j is ry. And it is equal to r times 1 cosine of theta y, or r cosine theta y. So cosine theta y therefore is ry over r. Substituting the value of ry and r, then we get theta y equals 44.30 degrees. So example 2, for the vectors a and b, determine the angle between them and the magnitude of the resultant vector. Then number 3, the cross product of a with b. So solution for the angle between them is simply apply the product. So remember that a dot b is simply the sum of product of corresponding components, and that's it. So a dot b is equal to negative 486. So the expansion is magnitude of a. This is the magnitude of a, square root of 24 squared plus 18 squared plus 27 squared. The second one is magnitude of b, then the cosine of the angle between them. So cosine of theta is negative, therefore it is more than 90 degrees. So theta is 108 degrees. Letter B, the magnitude of the resultant vector. So 8 plus b is simply 24 plus 21i plus quantity negative 18 plus 7j plus quantity 27 plus negative 32k, which is 45i minus 11j minus 5k. So minus 5k. So r therefore the magnitude is square root of 45 squared plus 11 squared plus 5 squared. The magnitude is 46.59 units. And finally, a cross b is simply obtained by arranging the first vector, then second vector in matrix form, and evaluate the product. So for I, negative 18 times negative 32 minus quantity 7 times 27i. And then for j is 27 times 21, then minus negative 32 times 24, then for k, 24 times 7, then minus 21 times negative 18, and the result is 387i plus 1337j plus 546k units. So these are the sample for applications of dot product and cross product. And what is important is we will apply this to forces for systems. So I hope that you have understood the presentations, and if you want to study more, then I want you to proceed to lecture 5 of this series of lectures. Thank you.